Hi, in this talk, we'll present an overview of the REANNZ High Performance Computing or HPC service and its associated tools and services while providing basic instructions for accessing the HPC and getting started with running your work on the platforms. If you have any questions about the REANNZ HPC service, please don't hesitate to reach out to us by emailing us at support@nesi.org.nz. The REANNZ HPC service works to support users from across a broad array of disciplinary backgrounds, with members of our own support team having experience in fields from biology to engineering to help in this endeavor. The REANNZ HPC service itself consists of four main subservices, those being the HPC compute service itself, which focuses on providing access to the compute resources for our users, whether that be large amounts of CPU, memory, or GPUs. Our data transfer and sharing service, which focuses on transferring data to and from the platforms and making sharing data between researchers as easy as possible. Our training service, which focuses on providing high quality training for the skills necessary to access and utilize HPC resources to the best of our users' abilities. And our consultancy service, which seeks to provide more in-depth computational support for our users than can be offered by our more general support. In this talk, we will go into more detail about each of these services and how you can access them to best help you utilize them for your research. The first thing we need to understand is exactly what is an HPC or high performance computer, and how is an HPC different from a standard laptop or desktop. The biggest difference between your standard computer versus an HPC is generally the scale. While your personal laptop or desktop might have 4 or 8 CPUs and 8 or 16 gigabytes of memory, an HPC, which is often used interchangeably with terms like supercomputer or cluster, is made up of tens or hundreds or thousands of nodes, sometimes called hosts, with each of these nodes being larger than a standard computer. The standard node size on the REANNZ HPC is about 126 and 166 CPUs, with memory ranging from 0.5 to 1.5 terabytes. These nodes are connected to each other via a purpose-built high-speed interconnect, which is much faster than if you just plugged in a bunch of computers together with Ethernet cables. Further, the hardware and software architecture of the HPC is purpose-built to obtain the maximum performance when running parallel codes. All of this together means that if your workflows are able to utilize multiple CPUs, you can generally achieve better performance than would be possible with the same resources in a non-HPC environment. So what compute resources do we have available? Currently, the REANNZ HPC consists of about 130 nodes with about 19,000 CPU cores and 92,000 gigabytes of memory between them. We also have 48 GPUs, 8 of which are our very high-performance H100 GPUs, which we provide. And while most of our nodes are around 0.5 terabytes of memory, we have specialized nodes with up to 6,000 gigabytes of memory available for those memory hungry workflows. You can find more details about the available resources on our hardware support page, which is linked on the slide. You should be able to find a link to the slides in the video description. So how do you get access to these resources? For those of you who are at a Tuakeri federated institution, which covers most of our users, with most New Zealand tertiary institutions and many major nationally funded research groups already being Tuakeri federated, all you need to do is go to the MyNesi website at my.nesi.org.nz, and you'll be prompted to log in with your institutional credentials through your institution's login portal. You will then be able to request a HPC user account. If you are not at a Tuakeri federated institution, you can still gain access, but you will need to fill in a request form at my.nesi.org.nz/register so that we can create a Tuakeri account for you, allowing us to set up your HPC user account. Once you have your HPC user account, you will then need to be a member of an active project to be able to use the HPC. If you'll be working with a colleague on an existing project, then your colleague can just add your user account as a member to their project, allowing you to log in and use the HPC with their project. If you'll be working on your own project, then you'll have to request your own project through the MyNesi website. If you choose to request your own project, then your project request will be reviewed by the REANNZ HPC support team. Once the review is complete, assuming there is nothing of concern, you'll be eligible for at least a small test allocation to determine if the HPC is right for you. Though your eligibility for a full-size allocation will be dependent on other factors. Now, once you have a user account and are a member of an active project, you're ready to start your work. But how do you even access the HPC? The most straightforward method to access the HPC is through the REANNZ On-Demand service. On-Demand allows you to access the HPC through your browser with no further setup required. all you need to do is go to ondemand.nesi.org.nz with your browser and log in with your institutional credentials. So here I am on the on-demand website, and so I can just hit login, and I've got my login credentials saved. So I will automatically log in, and now we can see the various apps that we currently have available, including JupyterHub, VS Code, Studio. But if you'd like to use the command line, you can do so by opening up the shell access here. Now, the first time you log in, there will also be an extra step that wasn't visible when I logged in there. You'll first need to set up a second factor, so make sure that you have an authenticator application like Google Authenticator on your phone. This second factor will be used alongside your institutional credentials to log into the HPC. You'll also be prompted on whether you trust the device you are using. If you're using a trusted device, such as your personal or work computer on your personal or work network, then you may choose to confirm to trust the device, and you will only need to log in with your second factor every 7 days afterwards. As an alternative option to using the on-demand service to log in, you can also log in via an SSH terminal. This will require some setup, but the instructions are very straightforward to follow. All you need to do is go to the standard terminal setup support page linked on the slide, then copy and paste the commands in order. So here, let me do that. I will copy the make directory sockets, and I'll go and open up my own terminal, bring it over, paste, and then I will copy the command to make the config file, and then open up my terminal again, hit paste. Now it's opened up Nano. So now, once that Nano's opened, I copy up this big block of text, and I hit paste. And now I need to change the instances of username. So there's an instance of username here, and I need to change it to my own username. Once I've done that, I can hit save. So I will hit Control X, and I will hit enter. Hit Y, and then I'll hit enter. And now I've saved my config file. Now that I've done that, I just need to run this command here to make sure that the permissions are all as they should be. And that's the setup. Now that you've set up your SSH config, all you need to do to log in is type SSH Mahuika, press enter, and you'll be prompted to authenticate via your browser. So if I control click to open this up, it will authenticate. I can say yes here, and then press enter. Now it will prompt me to authenticate again. You can make it so you only need to authenticate once with a setup, but I won't go into details about that setup. That's slightly advanced, but you can find it on the support page. And so once I've done this twice, I can press enter, and I'm logged in. Now, like with the on-demand login procedure, if it's the first time you've logged in, you will need to indicate trusting device and setting up your second factor. But afterwards, you will have the same login experience I had. Now, once you're logged into the HPC, you will have access to several directories. The first of these directories is your personal home directory, found at /home/your username. This directory is only accessible by you and the HPC support team. By default, it has around an allocation of 20 gigabytes, and you do not generally get this allocation increased, as the expectation is that you are not working very much within this directory. It is instead used for basic setup and configuration files. For each project you're a member of, you'll have access to two directories. The first of these being the no backup project directory found at /nesi/no-backup/your project code. By default, this directory has an allocation of 10 terabytes, and we can increase this as necessary if you require it. Files in this directory will be automatically deleted after being inactive for 90 days, though you will receive a warning email for any deletions occur, giving you a chance to retrieve any files. The purpose of this directory is storing data that can easily or quickly be regenerated or re-uploaded, and it's for active data and outputs for your jobs. A copy of important data generated in no backup can then be moved elsewhere for safekeeping. such as the third directory, which you'll have access to, which is your persistent project directory found at /nesse/project/your project code. By default, this directory has an allocation of 100 gigabytes, but again, we also increase this as necessary. The purpose of this directory is to install software, install data outputs, which you don't want to risk being deleted from no backup, but are still being used relatively actively. For home and project, we regularly take snapshots, which are maintained and can be found in the hidden .snapshots directory of each of /home and /nesse/project. Once you are in the .snapshots directory and selected the snapshot date you want to look at, you can then specify your project code or username and find the directory snapshot. Then you merely need to copy the required files back into your home or project directory. Snapshots may be taken of no backup occasionally and can be found in /nesse/nobackup.snapshots, but they're not guaranteed and are deleted as required. For longer term cold storage requirements, we also offer access to our freezer tape storage service where you can store currently inactive data on tape. There's no default allocation for freezer, but are instead granted as requested. Once you've logged in and know what directories you have access to, you will need to transfer data onto the HPC. For those of you that are using on demand, you can transfer data by selecting the Files drop-down menu, navigating to the directory where you want to transfer files to and from, and then using the upload and download buttons. For those of you using the SSH terminal, assuming you have followed the recommended terminal setup, you can transfer files with the SCP command shown on this slide. In addition to these methods, Globus is also available and is a recommended option for those with large amounts of data to transfer, or if you have connection consistency issues or data security concerns. I won't go into Globus setup details here, but you can find detailed explanation for its setup on our support pages. Now, on the topic of actually running through your work on the HPC, while you can run computationally small or interactive work through the on-demand apps and on the login node, the amount of resources you can access through these methods is very limited, with most of the compute resources only being accessible through batch jobs submitted to our queue scheduler Slurm. This means that if you want to do anything computationally intensive, you will need to know the basics of creating and running jobs with Slurm, which we'll cover in this section. To effectively utilize Slurm, you'll need to have some basic background knowledge in the use of the Unix command line. We will not cover this knowledge in this talk, as there's already a wide variety of resources which do this very well. But if you'd like to learn more Unix command line, we would advise the software carpentry lessons linked on this page. You can get away with just the first 3 lessons if you don't want to invest the time doing the full workshop. In addition to this, we have cheat sheets for both Slurm commands and Unix commands linked at the bottom of the page. Now let's look at some of the most important Slurm commands that you'll be using regularly. First is the sbatch command. This is the command that you will use to submit your job scripts to the queue. In the coming slides, we'll show you how to make your job scripts. In the event that you submit a job but realize there's an issue with it, you can also use the scancel command on the job ID to cancel or kill the queued or running job. When you submit a job with sbatch, you'll be provided your job ID, but you can also find the job ID with either of the next 2 commands. First of these being sq. Once you've submitted a job, you'll probably want to know the current status of the job in the queue. This is where sq comes in. sq by itself will show all the currently queued and running jobs. So you'll probably want to use sq with the option --me, which will only show your own jobs. You can see whether a job is pending or running in the state column, and as soon as the job completes, it will no longer be shown in sq. So this is a great tool for keeping track of which of your jobs are left to run and which ones have completed. For looking at your completed jobs, you'll want to use the saccount command. By default, saccount alone will show you pending, running, and completed jobs over the last day, but you can specify showing jobs since a specific date with the -S option. The most useful columns are the elapsed column, which shows how long the job ran for, the alloc column, which shows the number of logical CPUs, which is double the actual number of CPUs. If you're interested in more depth explanation of what logical CPUs are and how they're different from the physical CPUs, you can check out our simultaneous multi-threading support page linked on the slide. But all you really need to know is that often CPUs will be referring to logical CPUs instead of physical. So that will be double the actual number of physical CPUs. Next is the total CPU column, which shows the total logical CPU core hours spent working, and the max RSS column, which shows the maximum memory used at any points. You can use these SACOUNT options to analyze the utilization of your jobs and help understanding if you can request less of any of the resources for your future jobs. But often you can get away with using the next command to do these calculations for you. So that next command is nn underscore ceph, which will generate the summary of the CPU, memory, and wall time utilization of the specified job. So it's worth noting that nn ceph is not a real Slurm command, but a custom command for our systems. So if you try using it on other systems, it probably won't work. But we thought it's still worth covering in this section. Now that we have covered some basic Slurm commands, let's take a look at writing some basic Slurm job scripts. When writing your own Slurm scripts, the first thing you will need to do is add the line hash exclamation slash bin slash bash dash e. This essentially is just specifying the language bash. But the dash e option is worth being aware of because what it does is it sets it so that if any one job step fails, the entire job will fail out rather than having it continue on to each step and probably fail every subsequent step. So this can just save some time and resources by having the job fail quickly rather than try and do everything when one step fails. You can remove it if you need to, but generally we advise keeping it in. The next three lines all start with the same hash sbatch. This string starts with a hash indicating that it's a comment. But sbatch will read these sbatch comments and use them as options for the sbatch command. The first of these sbatch options is the dash dash job name, which I'm sure you can guess is the job name. Job name is arbitrary. You don't really need to worry about it too much, but it is useful to ensure it is something meaningful for you, as when you're trying to find details about some of the older jobs you've run, having a meaningful name can just make it easier for you to track them back down. The second option is dash dash time. This is the maximum wall time for the job, given in units of hours, minutes, seconds. Your job can run for less than the requested wall time, and on completing, the resources will be put back to the pool to be used by another job. So you won't be wasting resources if your job finishes early, at least not directly. But if your job is still running when the wall time limit is hit, then the job will fail out with a timeout error. For this reason, it's worthwhile to ask for maybe 20% more wall time than you expect to require, just to avoid potential timeout errors. Though if possible, we do advise you want to avoid asking for too much more wall time than you expect to need, as not only will it make your jobs queue for on average longer, it will impact the efficiency of Slurm stacking jobs effectively, of queuing all the jobs together, because if you have inaccurate wall time requests, it doesn't know how long your job's going to be, so it won't be able to stack all the other jobs into the queue as efficiently. It's not a huge amount of waste, but it stacks up on everyone doing their jobs. The final batch option here is dash dash mem. This is the memory per node with the default units of megabytes. Here we have asked for 1 GB of memory for our job. Memory, unlike wall time, is reserved regardless of whether it is used. So it is more important to ensure that the requested memory is accurate than wall time. Though it's still worth probably requesting maybe 20% more than you expect. As like with wall time, if your job tries to use more memory than it's requested, it's going to fail out without a memory error. But being a bit more accurate is still worthwhile here too. You may have noticed that we've not specified how many CPUs we want for this job. Since we've not specified this, the job will default to running serially with a single CPU, so you only need to specify the number of CPUs if you intend to run a job that utilizes more than a single CPU. Now that we've specified the resource dimensions and the job name, it is time for us to write what we want the job to do. In this case, we are just having the job run the pwd command, which stands for print working directory. Once you submit this job with sbatch, it will go into the queue. Once it reaches the top of the queue, Slurm will set up the job's environment based on the sbatch options you specified. In this case, a single CPU with 1 GB of memory for an hour. Then it will run all the commands you specified, in this case pwd, and write out the output to the output file. By default, the output file will be called slurm-jobid.out, whatever your job ID is, and will be created in the directory you submit the job from. In this example, the output of such a file would just be the output of pwd, so printing the current working directory as shown in the little black box on the screen. But that was just a serial job, and while you can run serial jobs on the HPC, serial jobs can generally be run fine on most people's local personal computers in most cases. The reason most people are using the HPC is because merely running jobs serially on their local machine does not produce the results in a reasonable time frame for them to get their work done that they need to do. And that is where parallelization comes in. Many scientific software applications are written to be able to take advantage of multiple CPUs, but such parallelization generally must be explicitly specified in the script. There are three main types of parallelization that we will look at in the upcoming slides. These are multi-threading, distributed programming, and independent job arrays. Which type of parallelization is available for your work will depend on the software that you are using. Now let's take a look at the first type of parallelization, multi-threading. Multi-threading is a method of parallelization where a primary thread forks a specified number of worker threads, with tasks then being divided among those threads. These threads will run concurrently within a shared memory environment. This means that multi-threading is limited to working with CPUs on a single node, as communication relies on the shared memory environment. And while this is a downside in that you'll be limited to the number of CPUs available on a single node with just this form of parallelization, this method of parallelization offers the upsides of a generally more efficient communication than other methods of communication between nodes or parallelization between nodes, and it can reduce the overall memory requirements so the task can share memory on the node rather than need the same data bit written to memory multiple times. This type of parallelization is ideal for any job which has the optimal number of CPUs being fewer than a single node, or for any job that has very high memory requirements, such as many genomic pipelines. Taking a look at a multi-threaded Slurm script is largely the same as a serial Slurm script we just covered. The only difference is that we are now specifying the number of CPUs we want with the CPUs per task line. In this case, we are requesting 2 CPUs. CPUs per task specifically refers to the CPUs available on a single node. So the maximum number of CPUs you can request here is the total number of CPUs on the type of node you want to run on. Another change we've made to this example is what the job is actually running. Rather than simply running pwd, which would show the same output as a serial job example, we have this command which you don't really need to know anything about other than it will print the current affinity list of the job, that list of IDs on the node assigned logical CPUs. So all the logical CPUs assigned to this job. In this case, from the output, we can see 4 logical CPUs assigned to the job. So as I mentioned earlier, the number of logical CPUs is double the actual number of physical CPUs. So from this, we can see that we've actually got 2 physical CPUs. So when you submit this job, once it reaches the top of the queue, Slurm will assign it 2 physical CPUs and 1 GB of memory located on the same node for up to an hour. Then it will run the specified code and exit out, returning the resources back to the pool after completing. Next, let's take a look at a distributed programming method of parallelization. MPI, which stands for Message Passing Interface, is the most common implementation of distributed programming. It allows for communication not just within nodes, like multi-threading methods, but across nodes as well. This allows your job to potentially access many more CPUs than would be possible with multi-threading alone, making it perfect for CPU-bound tasks, which just require more CPU processing time. Weather, geological, and molecular modeling are examples of tasks that often benefit from this method of parallelization. However, this method does have downsides. The first of these is that tasks can only operate on local data, so data will need to be read into memory on each node, and any data generated by one task will need to be communicated by other tasks that require it. So if you have a very large amount of data, generate a very large amount of data that needs to be shared between tasks, MPI may not be feasible. The second downside is that the communication method is generally not as efficient as multi-threaded communication methods which utilize shared memory. For this reason, it is common for jobs which utilize MPI to still utilize multi-threading within nodes where possible. Now let's take a look at an example of a MPI job. Once again, the script is largely unchanged from the serial example and the multi-threaded example, but let's go through the differences. First, rather than using CPUs per task to specify the number of CPUs, we are instead using N tasks. This refers to the number of MPI tasks. The task can be assigned to the same or different nodes if we're not forcibly specifying the number of tasks per node with N tasks per node. Next, because we're using in tasks without specifying a number of tasks per node, we don't know how many tasks will end up on each node. This means that using dash dash mem to specify the memory will not work how we desire, as dash dash mem refers to memory per node specifically. So if we end up with too many tasks on a node, we might run out of memory, with us wasting a lot of memory if the tasks end up being spread out on more nodes than we're expecting. For this reason, we change how we request memory to dash dash mem per CPU, which specifies the amount of memory available on a node to be proportional to the number of available logical CPUs. So you will receive double the number you request with mem per CPU for each physical CPU. In this case, that means receiving 1 GB of memory per physical CPU. So 2 in total, 1 for each task. The final change is we need to prefix any code we are executing with the srun command. Without srun, your code will only be executed on the primary task, with all other tasks remaining idle. Here we can see that the job is running 2 tasks, each with 1 GB memory for up to an hour, and each task will execute the command pwd. And so looking at the output, we can see that it has printed the working directory twice, showing both tasks executed the command. Now let's take a look at the last form of parallelization, independent job arrays. The truth is that this method of parallelization is not a real form of parallelization, as unlike multi-threading and distributed programming, there is no communication between tasks. Instead, arrays are a method of efficiently iterating on a task. This method is ideal for what are known as embarrassingly parallel tasks, where you essentially just need to do the same thing over and over and over again. For example, if you need to run the same workflow over multiple datasets or with different inputs, this method can allow you to submit a single array job rather than being forced to write and submit multiple jobs. As I mentioned, there is no communication between tasks, and they may not even run at the same time. And the order can be completely different and arbitrary. So if your jobs require communication between tasks, this method will not be feasible. Now let's take a look at an example of an array job. This job is effectively just a copy of the initial serial job we ran. The only difference here is that we've added the dash dash array line, which essentially specifies how many times you want this to submit the job. But you don't just want to submit the same job multiple times. Each iteration needs to be different somehow. And the way you do this is by using the environment variable slurm underscore array underscore task ID underscore ID. Each iteration of your job will have a unique number for the slurm array task ID environment variable, from the range you specify with the dash dash array option. So in this case, the unique number will be 1 or 2. On top of executing the pwd command, we are also printing the slurm array task ID variable here, so you can see in the output that both the working directory and the slurm array task ID has been printed, with the slurm array task ID being different between the 2 iterations. This slurm array task ID number can then be fed into your scripts and utilized to ensure that each iteration is doing something different. So for example, if you had a list of datasets to run an analysis on, you can specify in your script with the use of the slurm array task ID environment variable to determine which data to run on. So you've got 2 datasets. You say, if your slurm array task ID is 1, then run on dataset 1. If your slurm array task ID is 2, then run on dataset 2, and so on. It is worth also noting that each array iteration will produce their own output files. And so if you have an array of 1,000, you're going to get 1,000 different output files. And so you may need to work on compiling all that data together after the fact. Let's take a look at some more SBatch options that you may want to use. First is the dash dash account option. For these examples, I've not specified which project these jobs should be submitted to. And if you're only a member of a single project, you won't need to either. However, if you ever become a member of more than one project, you will need to specify which project each job is submitted with, and you do that with the dash dash account option. Next is the dash dash output and dash dash error options. By default, the output and error go into a single file, this slurm-jobid.out file. However, if you want, you can use these 2 options to split the output and error into 2 different files and then rename them into something else. However, if you do wish to rename those files, make sure you include the %j in the output and error file names. The reason for this is because %j ensures that the name includes the job ID. And if you don't include %j every time you run the job, it will just overwrite the file with the same name. Next, you can use the dash dash mail dash user and dash dash mail dash type options to specify an email to be emailed with. and then specify when you want to receive those emails. This allows you to, at different points in when with jobs, to get emails such as at the beginning of the job or the end of the job, or when an error occurs, you can get an email which can tell you, oh, I need to jump online now and check out these jobs. You can find all the available options with the command man sbatch. As I mentioned when discussing MPI, you can force a specified number of tasks onto each node with n tasks per node. If you use n tasks per node, you could use this in combination with dash dash nodes instead of n tasks. And so you could say, I want 5 nodes and I want 8 tasks on each node. And that will make sure you get that many nodes and put 8 tasks on it. And you won't have to specify the number of n tasks specifically. If you'd like to use GPUs with your job, you can do this with the dash dash GPUs per node option, specifying the type and number is shown here. So in this case, A100:1 is for one A100 GPU. The final option we'll cover here is the dash dash QoS equal debug. This option will allow you to run a debug job with each project limited to 1 debug job at a time, and each debug job limited to 2 nodes of resources 120 minutes of all time. The reason to use this option is that the debug jobs have a massive priority increase, meaning that they will generally start as soon as the requested resources become available. We advise using debug jobs for testing your code before submitting full-size jobs, as there's nothing worse than submitting a job only to have it fail within a few minutes and need to resubmit and queue again. And most jobs fail within the first few minutes because it's usually, a spelling error or grammatical error or something along those lines, like you forgot to load a package or something. While some problems are embarrassingly parallel and can effectively scale linearly with the resources they are provided, many problems aren't and will not receive close to proportional speed up when you increase the resources of the job. And this is known as scaling behavior. There are many reasons for this nonlinear scaling, but there are 2 major reasons that we'll briefly cover here. The first major reason for nonlinear scaling is due to something called Amdahl's law, with no code being 100% parallel. Even if you have perfectly efficient speed up for the parallel portion of your code, meaning double the CPU, will halve the runtime. The serial portion of your code will at best be unaffected, and sometimes they'll actually slow down as you increase the number of CPUs. So as you speed up the parallel portions of your code, the serial portions of your code will make up a larger and larger proportion of the remaining runtime, eventually reaching the point where increasing the number of CPUs has negligible speed up. That's what you're seeing here. As the line increases with the number of CPUs, the speed up decreases until it flattens out. The second major reason for non-linear scaling is simply because there are costs to communicating between CPUs, regardless of whether you're using multi-threading or MPI, but it's especially true for internode communications like MPI. This means that as you increase the number of CPUs, the communication overheads will also increase, and can eventually mean that increasing the number of CPUs can slow down your code because you actually get more overheads cost than you get speed up from extra CPUs. This is actually shown in an example of someone's code from quite a few years ago that someone did on our old machine, where they would increase the number of CPUs, and then after 96 CPUs, it actually started slowing down when they added more CPUs. But regardless of the reason for nonlinear scaling, as a result, it is necessary to perform scaling tests in order to better estimate the resource requirements of your jobs before you submit them, as guessing will often result in your jobs not receiving enough resources and failing, or receiving too many resources and queuing much longer, and then wasting those additional resources, or in the worst case, asking for the additional resources and actually running slower than they would have if it asked for less. So how do you go about performing scaling tests? We have a more in-depth support page covering the process, so I won't go into too much detail here, but essentially you want to start off with a small scale test, which is representative of the full size jobs you are intending to run. Ideally, this test will be something you already know the resources it will require to run. So for example, you have run the job on your local machine, you know how long it took and how many CPUs and how much memory your computer had. Then you will run the small scale test on the HPC to test how its performance changes as you run it. And then you can increase the number of CPUs and find the optimal number of CPUs by saying at what point your speed up is negligible or not enough to be worth it. You can extrapolate from the data points you have if it's necessary. So maybe you only do tests with 2, 4, 8, 16 CPUs, and it's still getting good performance increase when you do that. You don't need to keep scaling up to 100 or hundreds of CPUs. You can potentially extrapolate out from that once the trend of the line becomes clear, as it should be, a curve which is slowly leveling off to not be producing as many returns. You'll then test how increasing the data changes the runtime and extrapolate out the runtime for a full-size job. So once you find out optimal number of CPUs, so maybe it's 8 CPUs or something, you will increase the size of your test data if you can, where you'll do twice the size of the data, 3 times the size of the initial test data, 4 times, etc., and then extrapolate that out to what the full-size data would be to see how long it would take with the optimal number of CPUs. If you can't get a test job running on your log machine, then you will need to do some trial and error on the HPC of getting a test job running there. It's okay if they fail. You just make your best guess of what it will be, and you'll have to waste a bit of resources, but that's fine. It's important. The point of scaling is you'll waste some resources at the start to save resources later on. And so if you need to run some test jobs that may or may not fail and increase them slowly until you get one that works, then once you have your test job running, then you can just do the steps I laid out before. And that's laid out on the support page. Ideally, the size of the data is also easily scalable. So, if you had a data set that's 100,000 rows, you might, scale down the data to only be 1,000 rows for your test data set or something. But some problems you don't scale down very nicely. And in those cases, you're going to have to make some judgment calls about how you scale the size of your jobs, whether that's something like commenting out sections of code or anything along those lines. Will have to be up to you to try and make your small tests. Though inevitably, when you're not just directly scaling down a data set, extrapolating out from this will probably be less accurate, and you'll just have to be aware of that. And you may want to add a bit more buffer on the end of your extrapolated out job. Now, regarding the software available on the HPC, there is already a lot of scientific software packages pre-installed by the REANNZ team on the HPC, and you can find a list of available packages on our support applications page, linked on this page. If you would like to use the software that's not already installed, then please feel free to try and install it yourself in your project directory or your home directory if you want, though generally we advise project directory. Though do note that the software will need to be a Linux version, and you'll likely be using the software via the command line rather than interactively. If you are having trouble installing a software package, then please let us know and we'll see what we can do to help. We can't guarantee that we can install everything, but we'll do our best to help you to ensure that you can get your work done. Regarding licensed software, while we can install licensed software, REANNZ will generally not provide or manage the software licenses. Instead, you or your institution will need to manage and provide access to your software license for use on the HPC. So that might be something like a license server. A few useful commands with regard to software are the module commands. Modules are a convenient way to provide access to different applications on the HPC, since it's not feasible or even possible to have every version of every software available simultaneously. Instead, specific software versions are contained within modules that are individually loaded as needed. To find the available modules, you can use the module spider command, as shown here. So module spider and then the module name. And it's a search function that will allow you to search and find all the various versions of a piece of software. And it's a pretty good search function. So like if I type module spider capital R, it's not just going to show every single package that has a capital R in its name. Instead, it knows that I'm searching for the R software package, and it'll show me all the different versions of R we have available. The module show command can be used to provide you with additional information about a specific module. So once you have the module name, you can use that. And module load is the command that you will use to load the module and all of its dependencies. Finally, there's module help, which can be used to find other module commands. Here is an example of a serial job loading and using the Python module. Since we've used the command module load Python here without specifying a specific version of Python, we will use the default version on the system, which is usually the latest version. To use a specific version, just use the full version name of the desired version as shown when you search for your software with module spider. We can then use the software-specific commands in our Storm script. In this case, we are using Python to effectively run the command that does the same job as pwd. However, you could instead write a separate script, which you call here with the desired application. For example, you might have a Python script, which you call test.py, and then you can use the Python command to run that. So Python test.py to run your Python script with Python. Now, while most of our use questions and problems can be solved by our support team, Sometimes users have questions and problems which go beyond the scope of what the support team can help to provide. Um, that is where our consultancy service comes in. They are a team of research software engineers, and they can help research teams with anything from code automation optimizations to helping your code make use of GPUs. Consultancies are not offered by default, so if you wish to have a consultancy, you'll generally have to request one. Though sometimes we will contact specific teams in various situations to discuss one with you. But if this sounds like something that you'd be interested in for your project, please do contact us at support@nesi.org.nz. We also now offer a newish service, the Researcher Developer Cloud, where we set up custom VMs for research solutions with compute and storage necessary for your work in a secure environment where we use identity management services to provide you with more control of how users can access your project. If this service sounds like it might be useful to you, then please contact us again at support@nesi.org.nz. On top of these services, we are also heavily invested in providing and supporting training and computational skills, with us running and maintaining our own HPC-related training, as well as collaborating and supporting groups running their own such training. We offer weekly drop-in office hours and record and upload much of our training that we provide onto our YouTube channel. If you're interested in finding out about what training events are upcoming, please either subscribe to the REANNZ training mailing list or check out our training calendar. If you're interested in collaborating with us to support training you are intending to run yourself, then please contact us at training@reanns.co.nz. We've just about covered everything, but there are a few more points I'd like to cover to wrap up this talk. First, with regards to data management and security, all of the data you store on our services is stored in New Zealand-based data storage and will only be accessible by your team and the REANNZ HPC support team. Regular snapshots will be taken of data stored in the persistent project and home directories, and Globus is available as an option for high-speed, secure data transfer on and off the HPC. However, if you have specific or more stringent data security and management requirements and access requirements, then that's what we have available, then please do contact us, and we will be happy to discuss if we can provide a more bespoke data solution for your project, as we've done with other projects in the past. Next, please be conscientious of the fact that the HPC is a shared resource and we wish to support as many New Zealand researchers and their projects as we can. So if you waste resources unnecessarily, those are resources that another project won't be able to use. So please try to be accurate with your resource requests, especially with CPUs, memory, and GPUs. Though memory and wartime requests should, as a rule of thumb, maybe request 20% more to avoid failing due to running out of wartime or memory. Additionally, please avoid doing anything computationally intensive on the logger nodes, as this is a shared node for users to set up their scripts and environments and submit their jobs from. If you need to run anything computationally intensive, then these should be submitted as jobs through a Slurm script. If your jobs are found to be wasting a significant amount of resources, or your processes are hogging the logger nodes and impacting the work of other people on the logger nodes, we may be forced to kill your jobs or processes, but if we do so, we will inform you by email. And finally, when you do have any problems or questions and you wish to send an email to us at support@nesi.org.nz, please try to include as much relevant information in your email as possible, as the more information you include, the less back and forth that will be required and the faster we can resolve the problem. The most important information to include in your emails include, but it's not limited to, the job ID, the path to your Slurm file, and the job output files, the list of commands you used, and the error message. As I mentioned earlier, we do have weekly office hours where you can drop in and talk to a member of the support team, which you can use as an alternative to sending an email. And that's all I have to talk about in this session. If you do have any questions or problems, please don't hesitate to reach out to us, and we'll always be happy to talk.